All right. So last section, we're talking about how the M creates bending stress, right? The internal moment M creates a bending stress of My over I. We already knew that the internal normal force N creates N over A uniform stress, N over A. And now we're going to talk about this V right here. This V creates a stress. You might be thinking we already know the shear stress, right? What was our old way of calculating shear stress? Tau is V over A. We use that for allowable stress design for chapter 1. Sizing pins, because that was a quick and cheap and easy way to get a magnitude of the amount of shear stress. But this was the average shear stress. This was assuming tau was uniform over the whole cross section. But do you see what is really happening? It is not uniform. It's not uniform at all. It's at a maximum right across the middle. It's at a maximum, where do you think? Across the neutral axis. And it's at a minimum, actually it is 0 at the very top and the very bottom. So if we want to know, hey, okay, what is the shear stress due to V right here? We need to be able to calculate that. So our new equation, which on your formula sheet, is tau is really a lot more complex than V over A. It is VQ over IT. VQ over IT. Box that in. Memorize that. That is the new way to find the stress at a particular point. VQ over IT. So let's just kind of write some definitions. Tau, of course, is the shear stress. V is the shear force. The internal shear force. Whatever, if you cut it right there, what's the shear force at that location? All right, Q, we're going to come back to. I is the moment of inertia about the cross-sectional area, or the moment of inertia of the cross-sectional area about the neutral axis. Okay, and so V and I are just at that cut, and for that shape, what's the V and what's the I? But Q and T, those might depend on, okay, am I looking at this point right here? Am I looking at this point right here? This point right here? Q and T could be different at different locations. Let me start with T because that's easier. T is the width of the cross section at the point you're interested in. So let's say, let me erase a lot of this. Let's say we're interested in this point right here. T would be this dimension right here. It's a dimension perpendicular to V. It's a dimension perpendicular to V. So you see V is straight up and down. My thickness would be left, right, horizontal thickness. All right, perpendicular to V. All right, and Q is something called the first moment of area we'll just call it the first moment of area, and we'll expand on that down here. First moment of area. All right, so the shear stress is VQ over IT. The V for where it's, what is the internal V at the cut. Q we'll talk about. I is just for that shape. You probably have already calculated at the very beginning of the problem. Hey, I've got this shape, this type of beam. Let me find the I of that cross section. T is the thickness. It's perpendicular to V. Perpendicular to V. So most times our V's up and down. That means our T would be horizontal, left-right thickness at that point. Okay, so let's talk about this Q, this first moment of area. All right, so if we wanted to know the Q, if we were interested in this green dot, if we were interested in the stress at that green point, okay, not this point up here, but the green dot that I was interested in, if we're interested, hey, what is the stress at that green dot? Then, well, the T at that green dot would be that thickness right there at that location. And the Q is going to be this Y bar prime A prime. Y bar prime A prime. So Q is Y bar prime A prime. First, let's expand on A prime. A prime is the area above the point you're interested in and away from neutral axis. So actually it's not always above the point, but it is the area past the point you're interested in. So let's say past the point you're interested in and away from the neutral axis. So for instance, if I'm interested in that green point, then my A prime inside of my Q is going to be the area, away from the neutral axis from that point. What if I'm interested in this point right here? If I want to know the stress in that point, and so if I want to know the Q at that point, the A prime would be that area. All right? A prime would be that area. Okay, now the Y bar prime is the distance from the neutral axis. Okay, it's not, so don't draw this. It's not the distance to the point you're interested in. It's further than that. It's the distance past the point you're interested in to the centroid of A prime. All right, it's the distance from the neutral axis to the centroid of A prime. All right, it's the distance from the neutral axis to the centroid of A prime. All right, we'll get some practice on that. A prime, I think, makes sense. It's the area away, every area past the point you're interested in. Y bar prime is not the distance to the point you're interested in. It's the distance past the point you're interested in to the centroid of the area A prime. Okay? All right. And so that's what gives this it's a parabolic distribution right here of the maximum is at the very middle and at the very edge is 0. Why is the very edge 0 in this calculation right here? At the very edge it would be 0 because think about this A prime. What would be the A prime right at the very edge? There is no area past the point you're interested in. And so even though your Y bar prime would be a large value, your A prime would be 0. So that's why your shear stress is 0. All right, and one last thing. We've been looking at the stress on the cut, right? We've been looking at the stress on the cut. But if I was to look at a really small cube, an infinitesimally small cube, right here, the stress on the cut would be equal and opposite to this stress on the top of this cube if I was looking at a differential cube right here. Just due to the sum of the forces, due to this, it's still in static equilibrium. So the stress, it's kind of interesting that the stress on the face would be the stress right here in between layers. For instance, if we had a stack of boards, a stack of 100 pieces of plywood, you know how the plywood would rub together right here. The stress on the face, the transverse shear stress, would be equal to the stress between longitudinal planes, the longitudinal shear stress. All right, but mostly we're looking at the transverse shear stress. All right, VQ over IT. Q is Y bar prime A prime. Got it? All right, so let's practice. Not the VQ over IT just yet, but let's practice this Y bar prime A prime on this next page for all these different shapes. All right. So we've got this V right here, and here's my cut. Here's my cross-sectional area. My Q is going to be Y bar prime A prime. I'm going to come back to Y bar prime. What is A prime? A prime would be that area away from the neutral axis. That area away from the neutral axis. So one thing here. Here's my neutral axis right here. Just note the neutral axis and thickness will be perpendicular to V. So you can look at this, 5 times out of 6, my V is straight up and down, so my neutral axis is horizontal. My thickness is going to be horizontal. We'll do this one right here, though, in just a little bit. So there's my neutral axis. It's symmetric. So it's right there at the middle. Okay, so this, I'll do this in green. That green area, A prime, would be 0.1 by 0.3. All right, and now my Y bar prime would be, if I'm interested in that point right there, if we look here, I would need to go 0.1 just to get to the point, but then I need to go past it to the centroid right here. So I would need to go 0.15, 0.15 for my Y bar prime. See that? And then let's just calculate the thickness. The thickness would be that dimension right there, 0.3. 0.3. So calculating that Y bar prime A prime is the hardest part in this VQ over IT. Okay? Let's look at this one. Right here. It's symmetric. It's symmetric, so my neutral axis would be right here. Alright, the A prime, so Q, Y bar prime, A prime. I'm going to come back to this Y bar prime. The A prime would be, do this in green, would be this area away from the neutral axis, 0.1 by 0.6. My Y bar prime. All right, can y'all get there before I do for this point right here? If I'm looking right here, I would need to go 0.3 just to get to the point. but then I need to go to the centroid of a rectangle, just in the middle of the rectangle, so I need to go halfway of that point 1. So 0.35 would be the y bar prime. And so that's what I would use as my Q. Y bar prime A prime. And for the thickness, just the thickness at that point, 0.6. Thickness at that point, 0.6. All right, this next one. So my V is sideways. My V is horizontal. So a few things. My neutral axis will be straight up and down. My thickness will be straight up and down. My A prime, so this Q, Y bar prime, A prime. I'm going to come back to the Y bar prime. The A prime would be that area away from the neutral axis, right? 0.1 by 0.4. And then my Y bar prime, okay, if this is 0.3 and this point is right here, I think I would need to go 0.5 just to get to the point, but then I need to go past it to the centroid. So the centroid would be at the middle. So this would be 0.1. I go 0.5 to get to my point, and then another 0.5 to get the centroid of A prime. And then the thickness would be that thickness 0.4. That thickness 0.4. And that's what I would use in the VQ over IT. If I was looking at point A, trying to find the shear stress at point A on that cross section. All right, let's look at the next one. Let's look at the next one. It is symmetric, so the neutral axis would be right there. Q would be Y bar prime, A prime. All right. So I have two options here. Okay, so let's see if I can do this. Q, Y bar prime, A prime. All right, I've got two options here. For my Y bar prime, A prime, I could look at just one of these legs, let's say, or I could cut it and look at both of these. So those are my two options. I could look at just one of them or kind of look at both of them. Let's see how that would change things. So if I just look at one, it's 0.2 by 0.1, and then the Y bar prime, I would need to go not just to A, but to the centroid past A. That's 0.25. All right, and if I'm just looking at one, I would only have one area, and my thickness T would be 0.2. My other option is to cut this all the way here. Cut this all the way here. And my A prime would be 0.2 by 0.1, and I have two of those. This Y bar prime would still be 0.25, but here the thickness, I would need to do the thickness of both of those 0.4. I need to do the thickness of both of those 0.4. So, and then when I do the VQ over IT, right, I'm multiplying it by Q, I'm dividing it by T. That's why the two, I've got double on top but double on bottom. So I would find the correct shear stress. Right? I would find the correct shear stress. So sometimes you've got an option of something right here to cut it all the way and find the Y bar prime, A prime of all the area past it. Or just look at one leg right there. You'd get the same stress, even though you've got different Q's and different T's. All right, let's look at this next one. Let's look at this next one. A lot of times it's important to find the stress, right here, where this is being glued together, nailed together. Finding shear stress right here might be important, especially because the shear stress on this face is also the shear stress, on the longitudinal, not longitudinal shear stress, where that top board meets those middle boards. So let's do the VQ over IT. So Q is y bar prime A prime. I'm going to come back to y bar prime, but the A prime, whoops, let me do this in green, would be right here, right? Because the neutral axis is right there. So this would be 0.5 base times height by 0.1. And then the y bar prime, let's see, I would need to go 0.15 just to get to point A, but I need to go past point A to the centroid. I've got 0.2 as my y bar prime. And so here is interesting part, the thickness. Well, the thickness so where's my point A? My point A was right there where the top board meets those middle boards. So I'm going to say just above A, the thickness would be this 0.5. But just below A, the thickness would be, all right, not just that one, not just that one, but that one, plus that one. Why do I need to do all three? Because of this A prime was that whole area right here. So that wasn't like this past one where I just only looked at one, and so I'd only need the thickness of that one piece of it. That A prime was, I cut across the whole thing. So anyway, for this thickness just below A, I would need to add 0.1, 0.1, 0.1, 0.3 right there, just below A. So with that one, if I say, hey, what's the stress at point A, you'd have to specify, hey, are you talking about the just above point A, just below point A? Because point A is kind of this discontinuity where it changes, the shear stress changes. We'll see that in the next problem. All right, and then this last one. Q, y bar prime, A prime. Okay, I've got two options. Or okay, so for point A, my old way of doing this would be, all right, let me find the A prime. What is A prime? A prime would be this area right here. It's kind of a T right here. This area right here, which is a T. I could find that not too difficult. But then the Y bar prime would be tough. You could do it. You would need to find the centroid, right? You'd need to take that to the centroid. And finding the centroid of a T, it's not too bad, but you'd have to do, the find the centroid. Use the centroid formula to find the centroid, because it's not just a rectangle; it's two rectangles. It's a composite body. Remember statics. So I think you could do that. I think you find the centroid, but there's an easier way. You can just break this up into two rectangles, and you can find the y bar prime A prime of one and the y bar prime A prime of the other rectangle. All right, so that's what we're going to do. So I'm not going to do it the old way, although you could and you'd get the same answer. I'm going to sum up the y bar prime a prime of each of any area a prime past the point A that I'm looking for. All right, so let's look at this first small rectangle. I'm going to come back to the y prime. The area is 0.1 by 0.1. And the distance to the centroid of that, let me do this in green. The distance to the centroid in that, here's the neutral axis. I would need to go 0.2 just to get to point A, then another half of that dimension, so 0.25. All right, plus the y bar prime a prime of that area. The y bar prime a prime of that area. All right, so I'm going to come back to the y bar prime. The area is 0.5 by 0.1, and then the distance to get there would be 0.35. 0.35. All right, so I wouldn't try to do that once. Just break it up into, if it's multiple shapes past your a prime is multiple shapes, break them up into smaller shapes. Just do the y prime a prime of that shape, the y prime a prime of that shape, add them to get together to get your Q. And then the thickness, of course, just be 0.1. All right. So finding that Q, I think, is the hardest part. But once you've got it, then VQ over IT. Then you can do it, no problem. All right.